All right, welcome everyone. Welcome to the UNC Virtual Science Festival. My name is Tamara Poles, and fun fact, I'm actually trying to play safe right now and exhibit proper COVID precautions, but I'm actually in this room by myself and I'm vaccinated. So I'm actually going to remove my mask so you can see my facial expressions. Yay! All right, welcome everyone to this awesome session where we're going to go on a journey and learn about amazing physics concepts. We're going to see awesome demonstrations, all led by our UNC physics department. And today we have two featured schools on this call, and they are LB Yancey Elementary School and J.G. Edwards Elementary School. Welcome, y'all. Thank you so much for attending. So today, if you have any questions, our featured schools can actually drop their questions into the Q&A function, or you can actually use your raise hand feature and we can unmute you and you can ask the question verbally to our scientists. How cool is that? And if you're tuning in on YouTube and you have a question, please feel free to email your questions to ncscifest@unc.edu. So let's welcome today our amazing doctors, Duane Deardorff and Dr. Dan Young, who will be leading physics demonstrations today. And also, before I kick it over to you guys, I want to say a big happy birthday to Dr. Duane Deardorff. Happy birthday! All right, so why don't you tell us what you're going to be doing today?
We are excited to be here with you all today. And I can't think of a better way to spend my birthday than to be here with you, having fun. We enjoy having fun with physics and sharing what we know with other people. So you're going to learn about how things move, how they interact, and some may be surprising. We'll ask you some questions and we'll have an opportunity for questions hopefully at the end. And we're excited to show you.
We're just going to have a little bit of fun today. Again, my name is Dr. Dan Young. It is a pleasure to meet you all. I am joined today by Dr. Duane Deardorff. And Dr. Deardorff is going to kick us off today. He's going to show you a few demonstrations and talk to you a little bit about the nature of forces and Newton's laws. Off you go, Dr. Deardorff.
So maybe all of you know about Newton's laws of motion, but just a little bit of a review here. Newton's first law is what we call the law of inertia. Objects at rest tend to stay at rest, like this ball that is just sitting there. But objects in motion tend to stay in motion unless acted upon by an outside force. Now you saw this ball slow down a little bit, and that's because the table has a little bit of friction due to the tablecloth here, and that causes a force on the ball to slow it down. Now Newton's second law of motion is what we call F equals ma. If there is a force acting on an object, it will cause that mass to accelerate. Now, if we have three different size objects, each of them will experience different forces due to gravity. So if I drop a ball, it will fall down under the influence of gravity. It has this gravitational force on it, but it also has mass that resists its impetus to move. It has that inertia that we talked about for Newton's first law. And it turns out that a given mass will experience a force due to gravity, and that same resistance to that movement, the inertia, makes the mass cancel out in this equation, F equals ma equals mg. And so as a result, objects with different sizes and different masses fall at the same rate. So if I have these two balls, they fall at the same rate. And if that wouldn't be possible, I would not be able to juggle these balls because they would be falling at different rates and it would be impossible to juggle them. But obviously, it is possible. So we like having fun with physics. Another way we had fun was just a year ago. We had another application of Newton's laws of motion that involved an action-reaction. But before I show you that, let me show you another example of Newton's third law. This for every force, there's an equal and opposite force acting on the opposing object. So if I blow this balloon up,
This one's great.
when I release it, the air inside is going to come out. So there's going to be a force acting on the balloon in the opposite direction, air is going to come out in one direction, and that's going to cause the balloon to go in the opposite direction. You ready for this? On the count of three, here we go. 3, 2, 1.
It's gone all
And-
the way to the back of the room.
And off it goes. Now you have learned a little bit about rocket science. So applying this Newton's third law, a year ago, I mentioned that we had an opportunity to break a world record right outside this building in what's called a Galilean cannon. And it consists of something like this. If I drop these two balls, the top ball will go up much higher than you might expect. So if I just drop it by itself, it doesn't even come up as high as the original height. But if I drop these together, the top ball goes significantly higher. If I do it back here, whoa, it can almost hit the ceiling.
It's gone.
And so the same idea can be extended a bit to 4 balls. And this is what's called a toy called the Seismic Accelerator. And each ball is successively smaller so that the smallest one can go really high. In fact, we broke the world record at 13.1 meters. So that's about 40 feet or about a 4-story building. So it looks something like this. That's when it doesn't work. Okay. Third time's a charm.
There
it goes.
Nice.
So as you just saw, the tricky part is getting it to release directly vertically. And so we use this apparatus behind me to allow the Galilean cannon to fall vertically and then hit at the bottom after being dropped about 20 feet and up to the 4th story to break that world record. And unfortunately, we can't show you that right here, but that was a lot of fun last year. All right, I'm going to send it back over to Dr. Young as he tells you about more energy conservation and transfer of energy.
Yeah, thank you very much, Dr. Deardorff. So I'm actually going to ask you to help me out a little bit, if
Yeah.
you would, please. So what I have here for you is this is just a light bulb. It's sitting in a holder. It's connected to a couple of wires. If you would hold that for me, Dr. Deardorff. And what this is meant to show you is, as you saw a little bit earlier, there was a lot of exchanges of what we call energy within the system. And energy can appear in a lot of different forms. It can appear in the motion of these balls, as you saw. I can also use this little device here to transform energy from one to the other. Watch what I'm going to do here. I'm going to take this little ratchet handle right here, and I'm going to turn it. This is going to apply mechanical energy to this little handle here, and it's going to be converted into the electrical energy of the light bulb. Watch this here. Look at this. This is transformation of energy from one form to the other. And it gets even cooler than this. I'll take this back. Thank you very much. Because you see here that the system is connected. In a sense, there's a way for energy to get from here to here. It could travel through the wires, in a sense. So now let me show you a way of transferring energy without needing direct contact. This is a little bit wild. Watch this. What I'm going to do here is I'm going to be using this device. Let me show it to you right here. Essentially what this is it's going to be something that is going to be producing magnetic energy. I have a little coil here, and it's going to spin up a magnetic field. It's going to wobble back and forth really fast, and it's going to provide magnetic energy to whatever I place it on. Now, what I'm going to do is I'm going to take one of these little rings right here. You notice there's nothing connected to this ring whatsoever. It's just a little piece of metal right here. When I place it on this device, there's going to be absolutely no connection. They're not going to be touching at all. But even though they're not touching, I can still transfer energy from one location to the other. Let me show you how this works. This is going to jump pretty high, so I actually have to place this on the ground. All right. So here we are. Again, my device is on the ground. I placed the ring on the top. The ring is not touching the device whatsoever. There is no physical contact. There's no way for it to transfer energy through touch. I'm going to press the button. Watch what happens here. Whoa, did you see how high this ring went? And again, look at this. There's nothing in the ring that connects it to the magnetic field. What's happening here is a beautiful process known as induction. The magnetic field that is being presented by this object is being directly transferred to this ring. It's giving the ring energy and allowing it to jump off of the object. Now, What if we changed up the object just a little bit? What did that object really need? You kind of see here that, well, this object is metallic and it's a continuous object. There's no breaks in it whatsoever. What if I tried this again and I used maybe some different material? This is a PVC ring, for instance. Do you think it's going to jump this time? Let's see if we can get it to jump. Let's watch what happens. Here's my PVC. Let's see if we can get it to work. And oh, nothing's happening here. I'm pressing the button, I promise. The issue being that this particular ring is not as good as absorbing energy as the other one. It turns out that within this particular PVC ring, right here, it is difficult to get current to flow within it. And current is the thing that absorbs the magnetic energy. What if I took my little ring here, and this time I'm going to give it a cut in the middle? What do you think is going to happen? If I place the ring on the device, is the ring going to jump this time? Think about it to yourself. Let's find out. Here we go. Let's see. Let's push the button. Oh, nothing. Again, interesting. And it's because this cut within the ring is not allowing current to flow. It is not allowing the ring to absorb electric energy or magnetic energy, in this case, from this particular device. Now, it's time for you to make a prediction. All right, we're going to do the jumping ring 2 more times. And I'm going to do jumping ring with, here's an aluminum ring. You see here. I am also going to use a copper ring that you see here. What I want you to think about is, which of these 2 rings is going to jump higher? I'll give you a hint. The copper that you see here, this copper ring is more conductive. It's easier for it, in a sense, to absorb energy from the magnetic field, but it's heavier than the aluminum ring. So this is what I want you to do. If you're able to do so, if you have the ability to open up the chat, what I would like you to do is, if you think that the aluminum ring is going to fly higher, if you have the ability to do so, please put the letter A in the chat. If you think the copper ring is going to fly higher, if you have the ability to do so, put the letter C in the chat. If you think that both of them will rise to exactly the same height, put the letter B in the chat. What do you think here? I'll give you a few seconds to think on this. We'll look at some chat answers.
We have some C's. We have A. LB Yancey says A.
Okay. A lot of mix here, a lot of mix. All right.
Yeah, it's a good mix.
Very good, very good. All right. So again, the fight between this is the aluminum ring is lighter than the copper ring, but the aluminum ring is less easy for it to absorb energy from the magnetic field. I see some guesses. We got a nice little representation of all of them. So now, how do we do science? We perform an experiment and we confirm our guess. Here I'm going to enlist the help of Dr. Deardorff. All right, we're going to start with the aluminum ring. Dr. Deardorff is going to tell us how high it's going to go. Are you ready? 3, 2, 1, boom. All the way up there. It's even off the screen how high that aluminum went. All right, let's try again with the copper ring. Here's the copper ring. Are you ready? 3, 2, 1. Not even close. Copper ring only got to here. The aluminum ring got all the way up to here. So how do we understand this scientifically? We understand this by saying, oh, well, even though the copper ring is heavier and it is able to conduct better, that better conduction, the ability of it to draw energy from the magnetic field, is not quite as good as the increase in its weight. The aluminum ring wins this particular fight. All right, one more thing I want to show you, and then I'm going to kick it back to Dr. Deardorff. All right. Now let's not trip on the cable. Dr. Deardorff, if you would give me a hand with this, please. All right. So Dr. Deardorff is going to take our jumping ring apparatus. He's going to hold it right there. And what I have for you is this little object right here. This is simply a light bulb that's hooked up to a couple of wires, but you notice that there's no battery here. There's no way for this light bulb to light. It's not plugged into the wall. There's no battery. I'm going to make it light by having it draw energy from the magnetic field. You ready for this? All right, tilt it forward just a little bit. Beautiful. And let's do induction. Look at that light bulb light. The light bulb is extracting the energy from the magnetic field and converting it into electric energy, which allows it to become brighter. All right, that is your electricity and magnetism lesson for today. I'm going to kick you back to Dr. Deardorff, and he's going to show you a little bit about rotations. Off you go.
So we already talked a little bit about how things can continue moving. That is the nature of this inertia. We could also think about it in terms of momentum. So objects will tend to keep moving unless there's some sort of an external force acting on them. And the same is true for spinning objects. So if I spin this plate, it tends to keep spinning unless there's some sort of an outside force at a lever arm, what we call a torque, that causes it to slow down. So even if it's on my finger here, get a little bit tricky, and back on the stick.
Oh, so
yeah. So if I put my finger here at the edge, friction times its radius is what we call a torque. It will cause the plate to slow down. So Newton's laws of motion work for both linear motion and rotational motion. So now if we apply that idea to some other systems that can allow for rotation, we can get some pretty interesting consequences. So I have here a glass, put some water in it. My question to you is, how can I turn this glass of water upside down without letting the water fall out?
Not possible. No way.
You don't think so?
No way.
I'm going to show you how. So maybe you can think about how this is possible. And while you're thinking about it, just see what the possibilities are and what could possibly allow that water to stay in this glass without it falling out. So keep thinking about that and just, nobody saw that? Okay, a little bit of water maybe.
It mostly stayed in.
Okay, we're going to come back over here to the center. So now I'm going to do the same effect with this platform that can be suspended here. So we have the glass, I swing it back and forth, and the water stays in. And let's see if we can go all the way around.
Hey.
Just like a roller coaster that does a loop-de-loop, as long as the speed is high enough, then the centripetal force, the center pointing force, will keep pushing on the bottom of the glass so that the glass and the water inside don't know any different than when it's just standing still. So that is what we call centripetal acceleration. So it's a special kind of acceleration that is similar to what you're experiencing now due to the acceleration due to gravity, but for a rotational state. So Dr. Young is now going to talk a little bit more about rotation and torque and something called angular momentum.
You betcha. All right, thank you, Dr. Deardorff. All right. So once again, I'm going to enlist the help of Dr. Deardorff for our next demonstration, and I'm going to have him sit in this chair right here, if you would please. All right. Okay, the next thing we have to do is, this is now going to be a discussion of what we're going to refer to as angular momentum. Things that are rotating have some momentum attached with them. And when you are in a rotating system, the amount of rotation that you have needs to be conserved, needs to be the same. This allows us to do really cool demos like this. You ready? All right. I'm going to spin it up. I'm going to give Dr. Deardorff some angular momentum. And watch. As he rotates the wheel, the platform begins to rotate as well. Watch now, he's going to rotate the wheel the other way. And he begins to spin back the other direction. The angular momentum that is present in the spinning wheel is counteracted by the angular momentum of Dr. Deardorff as he spins on the stool. Isn't that cool? This may actually be my singular most favorite demo in the entirety of physics. And let me show you something even cooler. All right. All right. Now, what I'm going to show you here is a beautiful idea in rotations. This is known as precession. Once again, I'm going to enlist the help of Dr. Deardorff, if you would please. Dr. Deardorff, give me a spin. Beautiful. Now this wheel is going to experience a gravitational torque, and we watch it precess. The angular momentum in the wheel continuously spins round and round and round as gravity applies a force, or as again we say, a torque to this particular wheel. This is a phenomenon known as precession. This is the reason why, for instance, if you're biking down the road and you want to turn to the left, what do? You lean to the left. That gives you a gravitational torque, which turns your bicycle. All right, now on to our next set of demonstrations. Follow me, please, with the camera. All right, next, what I would like to do is I want to make this balloon pop right here. It is currently sitting on a bed of nails. These nails are spaced fairly closely together. So you might guess, well, I really want to make this balloon pop. So what are we going to do? Let's add some weight to the top here. Let's see if I can get this balloon to pop. All right, let's see. Oof, these are heavy textbooks. Oh man, all right. Well, let's put one up here. Oh, that's okay. Well, I guess we need another one. All right, let's try another one here. Well, okay, let's try another one. Here's another book. All right, let's see. Let's get this balloon to pop here. All right, come on. Well, let's add some more weight. That's the solution, right? Just add more weight. Okay. All right, let's add some weight here. I guess it's got to be enough, right? Come on. What on earth? I promise you, there is a bed of nails that is sitting right here. So why is the balloon not popping? Because of all of the weight that is present on it. This is the difference between pressure and force. All of these books are very heavy. They're supplying a force to this balloon, but the force that is acting on the balloon is spread over a very wide area across all of these different nails, which means even though the force is very large, the pressure is very small. But I know what you want to see. I know. Let's get the balloon to pop. All right. So how do I get the balloon to pop? I need to increase the pressure on the balloon. Let me show you how I'm going to do that. All right. So here, let me show you previously, this was our bed of nails from earlier, very dense, very low pressure that they are exerting. I'm going to change it out for this bed of nails. You see here, much farther apart that they are spaced, they are going to be able to exert a much higher pressure as a result. So let's make the force the same, and let's see if we can increase the pressure to pop the balloon. All right. All right, let's see here. I'm going to use the same force, but by decreasing the area over which the force is exerted, the pressure goes up. See if we can pop the balloon now. Oh, it only took one book that time. All right, but do you see? Again, the force that I needed was less because that force is now spread out over a smaller area, which means the pressure being exerted goes way up. Now, every single one of you lives in a constant domain of pressure. You may not realize this, but every single one of us is living in a sea of atmospheric pressure. And this atmospheric pressure is very strong. Let me show you. Little rubber plate here. Yeah, piece of cake, nothing here. All I'm going to do is I'm going to take this rubber plate, bam. Okay, well, all right, so there is atmospheric pressure pushing down on this plate from above, and I've evacuated all the air underneath it, so there's no pressure acting on the bottom. Let's see if I can lift this off the table. Can't do it. Can't be done. This is the strength of atmospheric pressure. I can even use it to lift other things. Watch this. Let me place it on the stool. I evacuate the air, and due to the power of atmospheric pressure, I can lift the stool, no problem. For a few seconds anyway. All right. So now I've shown you the power of atmospheric pressure. To give you a little bit more of a explosive demonstration, if you will, I'm going to throw you over back to Dr. Deardorff, and we're going to finish our demonstrations today with a bang. Off you go.
Hello, everyone. We have here a clear plastic tube with a ping pong ball inside. And at the ends of the tube are some mylar film from a party balloon. And I'm going to set that down here in front of this Pepsi can. What's going to happen is that I'm going to turn on this vacuum pump and pump out the air from this tube. That's going to create a vacuum inside. I'm going to have the ball start down here at the far end on the left. And then I'm going to pop this end. That's going to allow air to rush in, accelerating this ball from one end of the tube down the length and hitting this can that happens to have a target right there. So we are going to smash this can with a ping pong ball and nothing. That is a vacuum. All right, so I'm going to put some ear protection on because this is loud for me. It shouldn't be too loud for you. Here we go.
Gonna take just a moment here. We got to remove the pressure. Okay, you betcha.
So you should be able to see that the ball falls faster as the air comes out because there's less air resistance. So that's how I can tell that it's pumped down. You may be able to see that the film is bent in. So I think we are ready now. So here we go on the count of three.
Right, I'm gonna get out of the way.
Whoop, whoop. Close your ears.
All right, I'm ready. Let's go.
Here we go. 3, 2, 1.
Whoa!
Let's see that can.
Look at this. Look at the damage that that ping pong ball did to this can. Wow.
That was really a blast.
There you go.
All right. Thank you all very much. And I think we have time for just a few questions.
Yes. Thank you all very much for your interest and for watching us today. This is an absolute pleasure to present all these demos for you.
That was amazing. Thank you so much, guys. I think you put a lot of magicians out of work because some of those things I saw at magic shows, but now that I know that it could be explained by physics,
The science.
yeah, it's all can be explained by science. That's awesome. So great. Well, for those of you watching on YouTube, if you have any questions, please feel free to email them at ncscifest@unc.edu. And we have 2 featured schools on the line right now that are able to drop their questions in the Q&A, or they can raise their hand and we can unmute you and you can ask those questions in person. And those 2 featured schools are LB Yancey Elementary School and JG Edwards Elementary School. And our first question of today actually came in via email, and it is, could you give some examples of how physics is used every day by agriculture?
Yeah, you bet. I can go ahead and take this one. So just off the top of my head, for instance, if you're thinking about needing to do irrigation in agriculture, you want to ensure that the crops that you're cultivating are receiving the right amount of fluid or receiving the correct amount of fertilizer every time. So one of the things you're going to be doing is a little bit of fluid dynamics to say, well, for example, I want to feed 5 different types of plants with the same pipe. If I want to get them all to a certain amount of water, how fast does it need to flow through the pipe? One good example. Another one could be if you're considering like the evaporation of fluid from a plant. For instance, this is a thermodynamics question. If I heat the plant up to a certain amount of temperature, how much fluid do we expect that it's going to lose? So how much do I anticipate I need to put back in? Do I want to recover that fluid by perhaps covering the plants with some sort of a plastic covering that can grab the evaporation and put it back into the soil? I could go on and on, but there's 2 good examples for you of the use of physics in agriculture.
That's amazing. I didn't even think that they were associated. I love that in science, they need each other. All sciences need each other. Science, technology, engineering, mathematics, they all combined. Super cool. We actually have an attendee with their hand raised. Lee County Schools, we're going to unmute you and we would love to hear your question.
Okay. Would the Pepsi can still be crushed the same amount if it had juice in it?
Would the Pepsi can still be crushed if it had Pepsi in it?
Ooh, that's a good question.
Oh, just water, just water.
I think a little bit of water at the bottom. was
Just to
all
hold
that
it
was in
down.
there. Yeah, we didn't want to spray Pepsi over the whole stage here, so we decided to fill it with a little bit of water.
He wants to know if it had, like, if it was full and like it was not open, would it still have, what would have happened? What would have been?
Ah, yeah, good
That is a
question.
good question.
Yeah, we might have actually broken the seal, and we might have had Pepsi all over the place. Yeah, that's a good question. We actually haven't tried that before, so that would be a good thing to try. Experimentation time.
What would the big difference be
Let's
there?
do
There's
it.
some extra pressure inside the can.
Yeah, that's right. The pressure inside the can would be a little bit stronger,
Yeah.
so it might not crumple as much as what you saw here. So
Yeah.
might not be quite as dramatic.
Maybe fly off a bit faster. Though.
But
Hard to say. Yeah, we'll have to try it for ourselves sometime.
But I have seen a ping pong ball cannon like this send a ping pong ball all the way through a soda can, clear through. So it can really act like a bullet.
That's super cool. Awesome. Well, we have a question from Miss Clark's class. Why is it important to have knowledge of forces and motion? Sorry, I messed up there. Let me repeat that. Why is it important to have knowledge of forces and motion?
Yeah, forces in motion apply to all kinds of different examples, not just rockets. I mean, that's one that maybe people think about, but for cars and planes and machines, just think about anything that is moving around you, even yourself. So biomechanics is really important. In fact, we both teach a class, actually a couple of classes that deal with biomechanics, and understanding how our bodies move, how different animals move, can help us maybe make new products or something that can be helpful for us to live as humans.
Awesome. All right. Well, we have another hand raised. I'm going to see. We have Travis with their hand raised. Travis, would you like to ask your question? Oh, we're not able to hear you, Travis. So no worries, Travis, you could just drop your questions into the Q&A and we will get to that. But from email, actually, we do have a question. What is your absolute favorite physics fact?
Oh, you're making me pick one out of all of the cool physics stuff.
Yep.
Man. Oh.
I'll answer that one
Yeah, let me
because
think a little bit more.
Dr. Young already said that maybe his favorite physics demonstration was the one that we showed with the rotation on the
I love
stool.
that rotating wheel.
That was actually something that got me hooked. I took physics in high school, and when the teacher asked for a volunteer, I raised my hand, and I was the one on the stool with the bicycle wheel, and I thought that was just so cool, and it stuck in my head all these years later. That got me hooked, and I haven't gone back since. I've stayed in physics all these years.
I think I'm gonna have to go with the universal speed limit is one of the coolest things I've ever learned. So it turns out that you can go as fast as you want in the universe, but you're not allowed to go faster than the speed of light. Nothing in the universe is allowed to travel faster than light does. And when you take that assumption, you start working with it, you get into some really weird ideas. And this is a realm of physics known as special relativity. So that's probably my favorite physics fact, is that we have a universal speed limit, which unfortunately means that, sorry, a lot of things that you see in like this, Star Wars and the Star Trek about the warp drives or instantly transporting from one place to the other. Sorry, it breaks our universal speed limit. That actually can't happen. Sorry about that. Sorry.
Wow.
Yeah, that's where the science fiction comes in.
Yeah, afraid so.
Man, how dare they? Well, that is awesome. We have another hand raised, and we have Lee County Schools. Their hand is raised. Would you like to ask your question?
If you had a half copper and half aluminum ring, would it go higher than the aluminum or lower than the copper ring?
That's a good
You're
question.
testing me now. Might have to have a back and forth with Dr. Deardorff with this one. I would imagine if it was a pure ring that is made of half and half, you would kind of get that compensatory behavior where the copper half of that ring would get to absorb a little bit more of the total magnetic energies compared to just a pure aluminum ring. So my guess would be that half and half ring would probably go higher than the copper ring, but not quite as high as the pure aluminum ring.
Yeah, I agree. I think they would go somewhere in between where I had my hands. So maybe about halfway between those two heights.
That'd be my guess. Mhm.
Yeah, good question.
I like that. Mhm.
Yeah.
These are awesome questions. I have
Mhm.
another awesome question. How was physics used when it was first discovered?
Kind of interesting because physics, in a sense, was developed over the course of a number of different centuries, where different things were discovered at different points in time.
In fact, we keep discovering
Yeah, we
new
keep-
laws of physics.
Yeah, exactly. So I would say that perhaps that the physics that was developed at the time reflected what was going on in the moment. So for instance, when we were discovering a lot about the nature of gravity, that really influenced our understanding of the behavior of the solar system. And one of the big problems that we first needed to figure out is whether or not the planets in the solar system are orbiting around the Earth, which is what a lot of early astronomers thought, versus whether or not they orbit around the sun. And us learning more about gravity in the late 1600s, early 1700s helped us answer that question and then kind of jump off into different realms. So it wasn't really as much of physics just kind of started one day. It's more kind of a gradual accumulation of knowledge, and that lets us learn something new, which then lets us learn something new, and hopefully we get a better idea about the behavior of the universe, the more things that we discover.
There's still a lot to know and understand, though,
yes.
because most of the matter around us, most of the material around us is not what we're familiar with.
right.
It's hidden from us. So we call it dark matter.
Mhm.
So maybe you've heard of a black hole. That's an example. And even more so, it seems like the universe is expanding at an accelerating
Yes.
rate.
Very
What in the
weird.
world is causing that?
Very
It should
weird.
be collapsing upon itself.
Mhm.
Gravity pulls things in.
Mhm.
But no, there's something pushing it out. So that is mysterious,
Mhm.
dark energy. There's a lot to be discovered out there.
Yes.
That is so cool. And everybody on this call seems to have amazing and wonderful questions. So we
Mhm.
have a lot of future scientists on this call because that's what scientists do. We ask questions and then we do experiments to figure out the answers. So we have two last questions. Our second to last question is, what if something were to break the speed of light? So remember earlier when we said we cannot pass the speed of light? What would
Right.
happen if it did?
Yeah. Don't know.
Yeah. This is one of those weird things where when you kind of get into that domain, the physics as we understand it begins to break down a little bit in the sense that, for example, we understand that we live in, if you like, forward moving time. Time always moves forward for us. It's the next second, now it's the next day, now it's the next month. Time is always moving forward. But if you study special relativity and you admit some of these objects moving quicker than the speed of light, you run into some really weird ideas. And one of those weird ideas is that objects can actually move backwards in time, which completely just doesn't make sense with our current understanding of how physics behaves. So things moving faster than the speed of light, unfortunately, just kind of break physics as we understand it. So until we come up with maybe better perspective of special relativity that can handle some of those ideas, at this point, seems like Einstein was correct, and nothing in the universe is allowed to travel faster than the speed of light.
That's so cool. And my last question is, for our future scientists on the call, if they want to become you when they grow up, what should they do?
I think that's pretty easy.
Mhm.
Stay in school and take lots of math and science classes.
Okay.
That's pretty much lots of study, and it doesn't take necessarily a lot of natural intelligence. This is something you work at. So this is not something that necessarily came easy for us. In fact, both of us have had to work quite hard
Mhm.
to understand some of these really complicated things, but with time and effort, you can master it.
And keep attending events like this, and you will learn more as well.
Absolutely.
Absolutely keep attending events like this. Thank you so much, Dr. Deardorff and Dr. Dan. And speaking of attending events like this, if you want to learn more about awesome science events or want some extra science content, go to ncscifest.org.